Okay, a few words about Professor Gross. He's a professor and former director of the Cable Institute of Theoretical Physics in the University of California in Santa Barbara. He received his PhD in 1966 in Berkeley, the University of California in Berkeley, and was professor at Princeton. With his student, Frank Wilczek, he discovered what today is known as the asymptotic freedom. Is a concept that was a breakthrough for the formulation of QCD and the theory of strong nuclear forces. He was awarded by the 2004 Nobel Prize together with Wilczek and Politzer. And but this is not all. He has done a number of seminal contributions to the theory of superstrings and other fields of theoretical physics. Today he continues doing research at the Cable ITP. And he was awarded by a number of prizes, among others, the Sakurai Prize, the MacArthur Prize, the Dirac Medal, the Oscar Klein Medal, the Harvey Prize, the EPS Particle Physics Prize, and the Grand Médaille d'Or in France, together with, of course, the Nobel Prize I already mentioned. He holds a number of the honorary degrees from a number of countries around the world. And this maybe would be enough for a presentation, but there is another aspect of Professor Gross's career that I think it deserves a special comment today here. I met him here in Bariloche when he came for an evaluation of physics in Argentina organized by the Fundación Antorchas, and then at the International Institute of Physics in Natal, in Brazil, and then at the Abdul Salam ICTP in Trieste. And these are just a few examples of Professor Gross' will and compromise to help science in developing countries. So I'd like to thank you, David, for your generosity. And I really hope you could come back many times to Bariloche, helping us doing more and better science, to strengthen our links with the rest of the world, the scientific world, and of course, to stimulate young people to come to this, what I think is a beautiful world of science. So thank you very much again. And now I leave you with your talk that is entitled The Frontiers of Fundamental Physics. Please. Thank you.
Well, thanks for that very generous introduction, and you know, I'm really pleased to be back in Bariloche and honored to have such a large crowd of people who are standing up. And I warn you that, you know, I have this tendency, depending on the audience, but you look like a very good audience, to talk for a long period. And so relax, and there's actually room here to sit on the floor if any of you are interested. And there's an empty seat here, which I just vacated, which somebody deserves to sit here, whoever is enterprising. Really, it's totally empty. Absolutely. Anyway, as you know, I was here 14 years ago to review Bariloche and the Institute as part of the last chapter of the Antorchas Foundation. And that was my first visit to Bariloche, and then, as now, I'm enormously impressed by the beauty of the place and the friendliness of the people and the atmosphere here. It's clear why, you know, as I was telling a reporter this morning, at least in my field, theoretical physics, when one looks at Argentina, you know, Bariloche really stands out as the place in Argentina. And and as far as I can tell, you're continuing that tradition. And I'm really very pleased, delighted to be back here. Me and my wife, this is her first visit to Argentina and to Bariloche, and she's enjoying it very much. So I was going to give a general talk about the frontiers of fundamental physics, and I do wish to apologize that I'm not really going to talk about all the frontiers of fundamental physics. There are many. I'm talking more about the frontiers, oops, wrong button. The frontiers in my own area in which I've worked most of my life, which is elementary particle physics. It's that part of fundamental physics that probes, tries to discover and understand the basic building blocks of matter, the forces that act on them. Now, this field is rather young in a way. It's only, I date, 100 years old. The first elementary particle, perhaps, was discovered by J.J. Thomson, the electron, but elementary particle physics as an experimental science and began really with Rutherford's discovery of the nucleus in 1911, which is only 105 years ago. Rutherford not only discovered the nucleus, but as I will try to explain, invented the way that we use to study elementary particles, to probe the structure of matter, the atom, the nucleus, and now quarks and leptons. The atom was still, in 1911, rather hypothetical. It was, in a sense, invented by theorists. No one had ever or could see an atom, but everybody by that time believes that atoms must exist. Thomson had extracted electrons from matter, so electrons were certainly part of atoms, but what the atom was a total mystery. And Rutherford, in order to probe the inside of the atom, invented a new technique which consisted of bombarding the atom with other particles. Now, Rutherford had received the Nobel Prize in chemistry for his work on radioactivity, and he used alpha particles that are emitted in radioactive transitions, whose mass and charge he knew, to probe the inside of the atom by scattering the alpha particles off gold atoms. And his students, Geiger and Marsden, would sit in a room for hours in the dark, so their eyes became sensitive light detectors, and they would detect the scintillation of the scattered alpha particles on a screen and measure how many particles came out at a given angle. Rutherford thought this was a good way to probe what was the electric structure of the atom as a whole, and was surprised by the fact that many particles were deflected back at a large angle. He famously remarked that this was as surprising as if you throw a stone at a tissue and it comes back at you. He concluded that there had to be, that the charge, the positive charge that neutralized the charge of the electrons inside the atom and had most of the mass of the atom, had to be localized, confined to a very small region of space. And Rutherford was also a good theorist. And he knew Maxwell's theory of electromagnetism. He calculated the probability. He calculated how alpha particles would be scattered off a gold nucleus. That cross-section is now known as the Rutherford amplitude, the Rutherford cross-section, for that reason. And he concluded from his theoretical calculation and the experiment that the charge, the positive charge of the atom and most of its mass is inside a region which had to be smaller than 1 part in 100,000 of the size of the atom. He discovered the nucleus. He also, in effect, discovered the structure of the atom, which led within 2 years to Bohr's model of the atom, introducing quantum concepts, which was enormously successful. Bohr could calculate the Rydberg constant and construct a reasonable explanation of the periodic table. And within another 10 years, that led to quantum mechanics and a incredibly successful theory of atoms, molecules, matter, biology, everything around us. But from my point of view, he discovered the nucleus. This teeny object inside the core of the atom, which contained all the positive charge and the mass. Now, the study of the nucleus and what it's composed of, and the study of the particles that make up the nucleus has occupied us then for the following 100 years, using essentially the same idea. If you want to probe what goes on inside the nucleus, you build enormous accelerators and scatter one particle off another to see what goes on inside, just as Rutherford did. We use, of course, these much bigger instruments like the LHC in CERN. This is a picture of the LHC, and much bigger detectors. But the idea, the basic concept of the experimental technique hasn't changed since Rutherford. Perhaps unfortunately, perhaps new ideas are needed, but we've been doing the same thing the last 100 years. Feynman once compared this to studying the structure of a Swiss watch by taking 2 Swiss watches and colliding them together and taking a picture of what happens after the collision. And you could, if you had to, could figure out, understand what exists inside the watch, what it's made of, all of these springs and cogs. But not only could you figure out what it's made of, but how it works. That was Rutherford's idea: smash alpha particles in the atom, see how they're deflected, figure out what the atom is made of. And that's what we've been doing ever since. Of course, as I said, we use much bigger microscopes or colliders. This is the Large Hadron Collider in Geneva at CERN. This is the airport at CERN. It's a colossal machine, 200 meters underground, 20 kilometers around. Protons are accelerated in both directions, and they collide at 4 places where the experimental detectors, which are enormous. Everything gets bigger when you want to look smaller. Why? That's bizarre. But it's because, of course, you need higher frequency radiation to see finer structure. The higher the frequency, the higher the energy of the beams. Particles and waves are the same, we know from quantum mechanics. So you need enormous energies to look at small distances. And since the collisions are so violent, they spew out hundreds and thousands of particles, you need very complex and enormous detectors to map out all the pieces of the watch. Now, Using Rutherford's idea with these ever increasingly complex and precise instruments has ended up at the end of the 20th century with giving us a very detailed theory of matter, of all the matter that makes up nuclei, atoms, molecules, tables, people. Within the atom, we've understood the structure of the atom, electrons, and nuclei, subject to the force of electromagnetism. In a quantum mechanical description of the atom, describes atoms with incredible precision. Within the nucleus, here blown up by a factor of 100,000, we first identified the constituents, neutrons and protons, and at the end of the 20th century, the constituents of the nucleon turned out to be quarks. Quarks and electrons are, and their colleagues, are our understanding of fundamental matter, elementary particles. More importantly, and more conceptually, more fundamentally, we've understood the forces that act within the atom and the nucleus. In addition to the force of electricity and magnetism, the two forces that act within the nucleus act on quarks. A strong nuclear force that holds the quarks together, and the weak nuclear force that changes one kind of quark to another and is responsible for radioactivity. The theory that describes all of these forces and the constituents of matter is called the Standard Model. Now, I don't like to name the Standard Model. This is really a very precisely defined theory. Here is the Lagrangian, or the equations that are necessary to sit down and, in principle, calculate just about anything you want to know and can measure in the real world. There are a few elements of reality that don't fit within the standard theory, and we grasp those with great passion. Those are our clues as to what lies beyond the standard theory. But this theory, should be called the standard theory, is incredibly successful. It is, in a sense, the best, most successful theory that physics or science has ever had. In a crude, fundamentalist way, in principle, we see no reason why just about everything that could be measured, with some exceptions we'll come to, is not described by this theory. It consists of two components. One is a list of the matter that makes up some of the matter that makes up certainly the matter we have observed so far on Earth, that makes up the physical everything around us. And those consist of quarks, which make up the nuclei of atoms, up and down quarks, which make up the proton and neutron, and two other families of heavier quarks, which, when produced in the laboratory, decay, are unstable, and decay very rapidly. But otherwise are very similar in their nuclear properties to up and down quarks. The electron and its companion, the neutrino, discovered somewhat later, that don't feel the strong nuclear force, but do, as do the quarks, feel the weak nuclear force and the force of electromagnetism. And two other families of similar objects. three families of quarks and leptons. Why does matter appear in this form? Why do they have a strange pattern of masses and mixings that they have? Those are not questions that the standard theory can answer. They are mysteries. They're one of the mysteries that forces us to continue in probing the basic structure of matter. But within the standard model, or the standard theory, we take the existence of these particles and their masses from experiment. The forces that act on these particles is the other component of the standard theory, the force of electromagnetism conveyed by the electromagnetic field or the quanta of the electromagnetic field, the photon. The strong force conveyed by 8 particles like the quanta of light, but 8 of them called gluons. They hold the quarks together. And the weak nuclear force, whose mediators are 3 bosons called W's and Z's. And there's one more ingredient in this standard theory, which is necessary and which was hypothesized to explain why the quarks and the electrons and the neutrinos have a mass. And that's the so-called Higgs sector, whose prediction of a particle called the Higgs particle was made about 54 years ago and was finally discovered 4 years ago, completing this whole structure. And as I said, this is a remarkably successful theory. As a theorist, you can ask, when is a theory going to break down? You extrapolate a theory and you find some place where it predicts nonsense. So we can extrapolate this theory as far as with everything we know, all the way to the Planck length, which is the smallest length imaginable. That is where quantum gravity, the quantum effects of gravity come in and perhaps distort space-time in such a profound way that we are convinced that something has to change at or before that point. And all the physics described by the standard theory, certainly electromagnetism, as well as the strong and nuclear force, as far as we can measure and observe, acts everywhere in the universe and describes all the phenomena, the physical phenomena that the non-gravitational physical phenomena that we measure or observe to the edge of the universe. So that, from the edge of the universe to the Planck scale, is 60 orders of magnitude. Now, we haven't tested that theory over 60 orders of magnitude. We're about 14 orders of magnitude short, or 15 from the Planck length. But there's no indication that the theory must break down. This is quite remarkable that one has such a comprehensive theory of fundamental physics. Now, I want to spend a bit explaining one feature of this theory, because one of the most remarkable discoveries, I think, is that all the forces, the non-gravitational forces that govern atoms and nuclei, and all the matter we've observed directly, is essentially the same kind of force. It differs, however, greatly in the way we see it manifested in macroscopic physics, in everyday physics, even at the scale of the atom. And I want to explain how that can be, and how the strong nuclear force and the force of electromagnetism can essentially, at heart, be the same kind of force, and yet look so different. This has to do with asymptotic freedom, of course, in QCD. So electromagnetism. Now, electromagnetism is the oldest, after gravity, the oldest force acting on elementary particles that we know about. And it is a theory of charged particles like the electron and perhaps its anti-electron, positron with opposite charge. And according to the theory of electromagnetism, the force between these charged particles is mediated by a field. If you want, a charged particle creates a field, the electric field that acts, exerts a force on another charged particle. Now, you all know that the force law between charged particles falls off, gets weaker when you pull them apart, stronger when you push them together. It falls off like the inverse of the square of the distance between the particles, just as gravity does, by the way. And the easy way to prove that, which I will remind you of, is by using the famous Gauss Law, which roughly says, well, which says precisely that if you take a charged particle, surround it with a sphere, measure the flux of the electric field through the sphere. So in the case of a sphere, that's the product of the electric field pointing out of the sphere over the sphere of radius r, which has a total area of 4 pi, which I'm neglecting, times r squared. That's equal to the charge inside the sphere. So if you have a charge all by itself, the field falls off like 1 over r squared. And the consequence of that is that you can pull charges apart, because the amount of work you have to do is the integral of the force, which is E times Q times R, and that gives you, saturates when charges become infinitely far apart. You only had to do a finite amount of work, which is how much energy it takes to ionize the system. So force falls off like inverse square law. For that reason, you can pull charges apart. For that reason, you can ionize atoms, pull electrons out of atoms, make them run in wires, do work. The Industrial Revolution. Now, what I want to explain to you is why you can't do that with quarks. The strong force is essentially exactly the same as electromagnetism, except that in the case of the strong force, so this is a quark, an up quark. The strong force has, instead of one kind of charge, it has 3 kinds of charge. Now, since it has 3 kinds of charge, we have to give them names, and physicists called them colors, red, white, and blue, or red, white, and green, depending on your nationality. So they have 3 kinds of colors. But the force, the classical level, if we forgot about quantum mechanics, and you put a quark here, a red up quark, and an anti-red up quark. So this quark has red charge, and this one has anti-red charge. They would set up a field, which we call the chromodynamic field, the field that's produced by this colored charge. And classically, it would be, again, a 1 over r squared field. the force between the quarks would fall off like inverse square law. And if that were the case, you could pull quarks out of protons. You could pull the quarks out of the nucleus and make them run in conducting quark wires. It would be a very interesting world. But you can't. And indeed, when quarks were first suggested back in the 60s as, it looked to some extent for that, not dynamically, but as far as mathematical labeling went, that neutrons and protons and other such particles were made out of quarks. The big mystery was, well, why don't you produce quarks? You smash nuclei together, quarks should come out. Just like when you smash atoms together, or even just rub your hand, electrons come out. So the reason has to do with the quantum mechanical properties of the vacuum. And I want to illustrate the point by considering the simplest of all physical objects, which is a simple oscillator. So this is an oscillator, a classical oscillator, a pendulum, if you want, at rest. Now, of course, a pendulum can move and it has energy, but the lowest energy state is the oscillator at rest in its ground state, we say. Classically, that's possible, but quantum mechanically, it's not. Because we learned in quantum mechanics, the Heisenberg uncertainty principle, that such a dynamical state can't exist, where you have this particle, if you want, which is both at rest, so you know where it is, and has no velocity, no motion. There is always in quantum mechanics some so-called 0 point, even in the lowest energy state, motion. And so that 0 point oscillation is characteristic of any dynamical entity, anything which is physical in a quantum mechanical world, including the vacuum, the empty state, where there's nothing. But what does it mean to be nothing? What it means is you have turned off, say, all the electric fields. You've surrounded this room by a Faraday cage. There are no fields present, but a field can be thought of as a collection of oscillators. In fact, an infinite number of oscillators, to be precise. And each one of them has this sort of 0 point oscillation. So in quantum mechanics, there's no such thing as a classical vacuum, which is empty, in which nothing is happening. It's not a good way of thinking about the vacuum. Rather, it's full of these oscillating fields, oscillating oscillators. So the strong force mediated by the chromodynamic fields in quantum mechanics is sitting in this dynamical vacuum. This is actually a picture of what the vacuum looks like at the scale of the proton. So the size of this picture is maybe 3 proton radii. And what these undulating blobs are depictions of based on lattice gauge theory in QCD, based on calculations of the theory of the nuclear force, the oscillations of the chromodynamic field in the vacuum. So these quarks just aren't sitting there in a inert, static, empty vacuum. They're in a complicated dynamical medium. And that medium has an effect on these field lines that are created by the quarks. And it turns out that the effect of that is that the vacuum is a medium which abhors having these field lines present. It tries to squeeze them as much as it can. So it squeezes these flux lines into a tube. It can't get rid of the flux lines because there are these sources. So it squeezes them as much as it can. And that's roughly the content of asymptotic freedom, or one of its implications. Now, if that happens, and the flux lines are in a tube, how does that affect the force between the quarks? Well, now we put the quarks at area R. We measure the flux of the field through an area, a ball that surrounds this quark. But the area that the flux lines go through is now fixed. It doesn't increase like R squared, it's fixed. And therefore, the force, the field, the magnitude of the field, or the force that is created times the area, which is now fixed, equals the charge, means that the force is constant. It doesn't fall off like 1 over R squared. And consequently, if you want to pull the quarks apart, you have to overcome a constant force. And if you pull them apart by distance r, the energy it takes increases linearly. So instead of saturating, the work you would have to do to separate the quarks increases without bound. And that is, here actually is what happens in QCD, where you separate quark-antiquark. You see the flux tube? This is calculation within lattice gauge theory. And that means that, as I said, you have to exert more and more energy. And physically, it means that the quarks are permanently confined within the nucleus, explaining why you can never pull a quark out of the nucleus. Why, when you smash protons together, no matter how much energy you push in, you can't really separate the quarks. So that was an attempt to explain in simple terms why at heart, classically, the same kind of theory, the only difference really being that one theory has one charge, electromagnetism, QCD has 3 charges, the same kind of force law. Because of the quantum properties of the vacuum, they lead to physics which is totally different. In the case of electromagnetism, we have this long-range force that can act over the size of a galaxy and create magnetic fields which are galactic size. In the case of QCD, the fields are all visible only inside neutral combinations of quarks, like the proton, which is a neutral combination of 3 quarks. And the remnant of that force is something like molecular forces that act between nuclei, between neutrons and protons. That's nuclear forces, and that falls off very rapidly, exponentially, with distance. Now, a theory like the Standard Model, or QCD, as I said, is extremely successful. I'll just show you examples of the tests of this theory. This is asymptotic freedom and its agreement with experiment. This is how the strength of the force, the nuclear fine structure constant, falls off and becomes weaker and weaker when you go to shorter distances or correspondingly higher energies. Recently, the standard theory has been subjected to unbelievably precise tests at the Large Hadron Collider over now this is 1,000 or a TeV of momentum transfer scattering experiments where the cross sections fall by 12 orders of magnitude, a million times, beautifully described by these standard model QCD. But for a theorist, the really pleasurable part of making constructing a theory or making predictions that agree with experiment is actually calculating something that is very fundamental, like your mass. So sometimes when I give public lectures, I ask the audience, young people, where does your mass come from? And they say, well, I suppose from the mass of the atoms that make me up. And I say, well, where does the mass of the atoms come from? And some of them say, well, it's the mass of the nucleus. Well, that's correct, but where does the mass of the nucleus come from? And I've already explained to them that the nucleus is made out of quarks. And then they say, oh, it's the mass of the quarks. My mass comes from the mass of the quarks. And I say, no. Quarks are almost massless. In fact, if we can as theorists, turn off the mass of the quarks, how would that affect your mass? I would become massless. No. It would maybe decrease your mass by 5%. And then I explained to them that most of the mass of the proton arises from just the energy, the kinetic energy of the quarks that are bouncing around in a confined region. Why confined? Because this force doesn't decrease. They can't escape because they're being held together by this flux tube. So they bounce around freely at short distances. Eventually, they can't get out. So simplest way to think of a proton and your mass is a confined region set by the scale where the force becomes strong, and the mass as simply the energy of the confined gluon field, the gluons, which are massless, rattling around inside this bag, and the kinetic energy of the quarks. Your mass, in other words, is a simply confined energy. This makes many people feel good, because if they realize they've gained a few kilograms, they've gained a few kilograms of confined energy. But it makes theorists feel good because you can calculate. Once you know where the force becomes strong, how big these objects are, you can calculate how much energy is confined in that space and calculate the masses of all the quarks, the particles made out of quarks, like the proton, the neutron, and all these particles which were being discovered when I was a graduate student, and nobody had the vaguest hope of ever being able to calculate them from first principles. So we have this standard theory, which is unbelievably successful, but I have glossed over problems, most important of which being experimental or observational. Like the fact that most of the matter in the universe is so-called dark matter. Astronomers have seen it via gravitational lensing or its effect on gravitational effect on visible matter, but we have no idea what it is. Neutrinos in the original standard, simplest version of the standard theory are massless. It's easy to give them a mass, but we're not exactly sure how that works. We see in the universe an excess of baryons over antibaryons, of matter over antimatter. That we should be able to explain. We also observe cosmic acceleration, whose origin is vacuum energy probably, but we're not sure. Theoretically, we're driven by a variety of goals to explain these observations, but also to unify the forces, to explain some of the parameters that are very unnatural and have to be built into the standard model, or the parameters that characterize matter, the quarks and leptons that we can't understand or predict or calculate. And then issues having to do with gravity and the structure of the universe as a whole, such as the vacuum energy, cosmic acceleration, the theory of inflation, and even more fundamental questions of cosmology. So these are problems, exceptions to the standard model, theoretical goals, which, set the stage for our exploration of fundamental physics. For many years, some of us have been very excited by the fact that a few of these problems could be solved, perhaps, by the existence of a new symmetry of space and time called supersymmetry, which is one of the main goals of the LHC, and I'll discuss that briefly. But for me, one of the primary goals for the last 40 years almost, since the completion of the standard model, was the search for unification. So the standard model has these pieces I described. It has two kinds of matter, quarks and leptons, three families of quarks and of leptons. And it has three forces acting within the atom and the nucleus. And these are like 5 pieces of a jigsaw puzzle. So if somebody gives you 5 or 500 pieces of a puzzle, there are 2 possibilities. You work hard, you put it together, and you see what the final picture is. Or the dog ran away with 10 of the pieces, and it's very difficult. You don't have all of the pieces. The amazing thing about the standard theory, which came together in a very short period of time, was that these 5 pieces fit together precisely into a very beautiful, simple structure, as if all the force and all the matter had a common origin of force and a common origin of matter. So these 3 forces are characterized by 3 symmetry groups with 1, 2, and 3 charges. But they fit together very nicely into a larger symmetry pattern with only 1 force. Now, by that time, we'd already understood how this could be. Because if all the forces are unified, they should look exactly the same. So how could you have all the forces unified and explain why they look so different at low energy? I explained to you why electromagnetism and the strong force, the strong nuclear force, look so different at low energy. I told you that that was because of the properties of the vacuum. Now, The vacuum, I told you, should be thought of as, a medium. And you all know that the properties of a medium can be changed, perhaps for example, by heating the medium. So you might take fill this room with water, that's fine, at room temperature. But if you heat this room, it'll no longer be filled with water, it'll be filled with gas. In fact, if you want to really experimentally, observationally see that that quarks and QCD are really very similar to electrons and electromagnetism and QED, all you have to do is heat this room to about 100 million degrees, and all of the nucleons that make you up will melt. The property of the vacuum will change, those field lines will expand, the quarks will come out of the nucleon, and you'll have a plasma of quarks and gluons, which looks very much like a plasma of electrons and photons. In fact, such a deconfined, unconfined plasma of quarks and gluons has been created for very short times in highly relativistic ion collisions at RIC in Brookhaven and now at the LHC. We can see the deconfined phase of quarks and gluons. At the energies or temperatures we can achieve today, it's actually it's more like a liquid than a plasma, but it's definitely deconfined. So you could imagine that at very high energies, things look like they're the same. And then as you lower the energy, there's a phase transition. The water freezes. Quarks freeze into nucleons. In fact, we believe that happened in the history of the universe a few days after the beginning, whatever that is. So symmetry breaking, we call it, a phase transition. On the other hand, the strong nuclear force is very strong, much, much stronger than electromagnetism, which is why, by the way, hydrogen bombs are so much more powerful than TNT. TNT is chemical electric bombs. Fission or fusion bombs are due to strong interactions, strong nuclear force. But that we explained as well, because remember, the force depends on the distance. It gets weaker at long distance, at short distance, or higher energies. So one could imagine that at very high energies, the force between the quarks, electric or strong, becomes the same. So with these conceptual problems eliminated, one can extrapolate what we know about the real world up to where we now observe, which is about here, to even higher energies or shorter distances. And the remarkable clue is that all of these forces seem to have the same strength at a very, very high energy scale, which is close to the Planck scale, this fundamental scale of physics, which is really defined as the point where the gravitational force becomes strong. Gravity is actually a very weak force in the atom, 40 orders of magnitude weaker than these forces. But gravity, the charge of gravity is mass or energy, so it increases very rapidly with energy, and at this scale becomes important. This, I think, is one of the most important clues for the unification of all the forces with gravity at this enormously small distance scale. But in this game of fundamental physics, you have to be careful. Looks pretty good, right? But it could be a coincidence.